Imagine taking a standard sheet of paper and folding it in half, then folding it in half again, and again. How thick do you think it gets if you keep going? If you could fold that single sheet just 46 times, the stack would be so thick it would reach all the way to the moon. That jump from a fraction of a millimeter to 300,000 kilometers is exponential growth. In mathematics, we calculate this rapid scaling using rules known as powers. Let's look at how they actually work. When dealing with numbers that multiply rapidly, writing out the same number over and over gets confusing. Powers give us a clean, strict mathematical shortcut. This diagram shows the anatomy of a power. The large number at the bottom, in this case 5, is what we call the base. This is the core number that is being multiplied. The little number up top is the exponent, or power. It tells us exactly how many times to multiply that base number by itself. Let's apply this to our paper folding. If we fold the paper 10 times, we are doubling its thickness 10 times in a row. Instead of writing out 10 twos, this is written simply as 2 to the power of 10. And as we saw with the massive stack of paper, that scales up fast. 2 to the 10th power equals 1024. There is a common trap here. 4 to the power of 3 is not 4 times 3. It is 4 multiplied by itself 3 times, yielding 64. Once you have multiple exponential terms in the same equation, you need specific rules to combine them, provided they share the exact same base. This graphic shows the two main operational laws. When multiplying terms with the same base, you simply add the exponents. When dividing them, you subtract the exponents. And if you encounter a negative exponent, you flip the expression to the bottom of a fraction, making the power positive. Let's see how they work together. To solve 2 to the negative 4th power times 2 to the 7th, keep the base of 2 and add negative 4 and 7. The result is a clean 2 to the 3rd power. Notice that negative powers do not create negative numbers. They are just instructions to create a fraction, shrinking the value down rather than scaling it up. Scientists use a specialized format called standard form to handle massive figures, like the distances between planets, without getting lost in a sea of zeros. This diagram shows the structure of standard form. It requires a number a between 1 and 10 multiplied by a power of 10. Take a real-world distance measurement in space, 70 billion 40 million meters. To compress this, we use the decimal jump method. We take the hidden decimal from the far right and move it 10 spaces left, parking it right after the 7. This gives us 7.004. Because we jumped 10 spaces to the left, we multiply that by 10 to the 10th power. We keep the 4 because non-zero digits are critical information. And because we moved the decimal to the left to shrink a large number, our exponent of 10 remains strictly positive. You now have the mathematical tools to handle both exponential scaling and astronomical numbers with precision. This graphic gathers all the core rules from the chapter: the anatomy of a power, the 3 operational laws, and the formula for standard form. Grab a screenshot of this frame right now. It will be your best reference when tackling practice problems. Remember that negative exponents make fractions, not negative numbers. Keep these rules straight, and you'll be able to calculate your way straight to the moon. You now have the mathematical tools to handle both exponential scaling and astronomical numbers with precision. This graphic gathers the core rules from the chapter: the anatomy of a power, the 3 operational laws, and the strict formula for standard form. Grab a screenshot of this frame right now. It will be your best reference when tackling practice problems. Remember that negative exponents make fractions, not negative numbers. Keep these rules straight, and you'll be able to calculate your way straight to the moon.